Bienvenidos a Lesson 44. So now we're going to talk about using our line to make predictions and other issues. So we did do a brief prediction for just a point estimate. So if we have a student with a 3.6 in high school, what do we estimate that their college GPA would be? We can calculate an interval estimate as well. So we're going to talk about that and also some issues that we also see in simple linear regression. So for here, we looked at, just here, first year college GPA students that earned a 3.6 in high school. We estimated that it's going to be 3.498 on average. We did that by plugging into that y hat is equal to, let me see if I can remember these numbers, 0.69-ish, 0.78 times 3.6. And we calculated that we think that students with a 3.6 in high school at this small university, on average, they get 3.498 in their first year of college GPA. So plugging in, yeah, that's how we did it. But this is just a point estimate. There's some variability, right? Not every single student that had a 3.6 in high school is going to actually get exactly a 3.498. That's very specific. There will be some fluctuation, right? So we'll have a number of students that had a 3.6 in high school. And we want to know like variability, like from student to student. So we can get an interval estimate. So we have two types of intervals that we can use here for prediction. So confidence interval and prediction interval, and I know this will sound a little wonky, so absolutely we'll go through both of them. So a confidence interval in this context predicts the average response for everyone in that population with that specific value of x. So this would be if I want to estimate or predict the average first year college GPA for all students who earned a 3.6 in high school. So that's the key thing. So confidence interval is for everybody, it's for the population, it's the average. So we're predicting the average for everyone. The prediction interval is more individual. So suppose now you have one student who, I don't know, just comes to the school and they had a 3.6 in high school. What about estimating that individual student's first year college GPA? So you would use a prediction interval. So you want to predict the first year college GPA of just a single student who earned a 3.6 high school GPA. So things to consider is for confidence interval, we want to estimate the average college GPA for all students that had a 3.6 high school GPA. In the second type, prediction interval, we want to predict the GPA of just one student that earned a 3.6. So student to student is going to vary a lot more than what we think the average of everybody varies. So if we took the average of everybody's college GPA that had a 3.6, that's going to be a much more precise estimate than if we wanted to estimate just one person who had a 3.6. Okay, so now we're going to give you a breakdown of the equations. This is not really something I feel like is super necessary to memorize, although the relationship to each other is important. So for a confidence interval, for mu y, so remember the confidence interval, it's for the true mean response of all individuals that have a specific value of x. So on the last page we were focusing on maybe the average college GPA of all students at that particular college that had a GPA in high school of 3.6. This is what we would look at. So y hat, so what's predicted, you plug in your value of x into your linear equation, you get a y hat, have a t star, and then times a standard deviation for y hats. Your prediction interval is for y, so not for the mean, but just for one individual. So one thing I really want to draw attention to here is you have your t star times this standard deviation of y hat. Here you have your t star times this square root of s squared plus s squared for y hat. The prediction interval is wider. Always. The confidence interval is narrower. Always. So and that's one thing we love to do, is we love to give two intervals side by side and say, oh, Kelsey calculated a confidence interval and a prediction interval for when the high school GPA is 3.6, but she forgot to label them. Which one is the prediction interval? That is something we love to do. We love to give you two of them and have you tell us which one it is, because we love to basically enforce that the confidence interval is narrower, the prediction interval is wider. That's all you need to know. We wouldn't be having you actually check the math or do the math by hand. This is something we frequently won't do by hand. We'll usually have R do it for us. This gets gross. Trust me, it really, really does. So the standard errors here, so in critical values, this is what I mean. We don't calculate these by hand. It's really, really gross. And but do know the t critical value, this would be reasonable, comes from a t distribution that has n minus however many explanatory variables you have minus another one. So here it'd be 10 minus 1 plus 1, so 8. So in practice, we're going to use software. This is not going to be something like even data analysis. This is not going to be something we give you. It is gross. So we would just use here. So here's my residual. So my S estimate here. This is my degrees of freedom. That's what we would use here. So this S that you use here. But once again, this is not something we regularly do by hand. I just wanted to show you this to show this prediction interval should be wider. Okay, so here we are. We're looking at the confidence intervals and prediction intervals. A lot of times they're depicted as bands. We did provide some R code if you want to visualize this for your own data set. So we're focusing on high school GPA of 3.6. And one thing to note too is the bands, they always have this shape. The closer to the center you are, usually the narrower the band is. The closer to the edges you are, the wider it gets. That's pretty standard for these. The bands usually do not run parallel to the line. So if I want to look at 3.6, and I want to look at, so my point estimate is where it meets the line. It probably doesn't match perfectly quite there. So this is supposed to be that 3.498. That's our point estimate. Remember when we plugged into the least square regression equation. So if I want to look at, it's slightly off. So I'm looking at this blue, the distance from one blue to the other. That is going to be my confidence interval. Looking here, this pinkish, that's going to be my prediction interval for someone with a 3.6. So one thing to note is the point estimates are going to be the same. This 3.498 for everyone here. And sorry if you have a previous copy of the notes, you might notice I corrected a typo here. So high school GPA. Should say high school GPA there. So looking here, I have the 95% blank confidence, 95% blank interval estimates the average college GPA. So average GPA for all students. This tells me, oh, this is going to be a confidence interval. So I kind of gave it away. I'm really, really great at telling the punchline before the joke. And yeah, it's just never great. with so a high school GPA of 3.6 to be between, and I'm looking here and here. So I have R, so between 3.35 and 3.61. That's roughly where these will line up. If you plug into R, that's what they'll give you. So then looking here, the 95% blank interval predicts the college GPA. So not the average, just the college GPA for a single student. So this is going to be a prediction interval. With a high school GPA of 3.6. So now I'm looking for this value and this value, like where they line up here. So to be between 3.05 and 3.498. Oops. I just put the other thing. 3.90. My bad. Sorry about that. So we predict, so this should line up roughly. I know I don't have it quite lined up with those lines. 3.05 to 3.90. And the point estimate should be the same. So whether you're doing a confidence interval or a prediction interval, your point estimate will be the same. It'll be plug in 3.6 into that line equation, and what you get is the 3.498. However, then the plus or minus bit makes the prediction interval a bit wider. So anytime that we give you two intervals, you should always be able to say, oh, well, the wider one's the prediction and the narrower one is the confidence interval. We would not, on an exam, require you to calculate one because it really would require coding or some really just excellent algebra skills, but that's not what we're testing here. So here's another example. Definitely feel free to take a pause here before I go on. So the blue, that's my my confidence bands. The pinkish purpley, that's my prediction band. So from the plot, what is the prediction interval for x equals 3.2? So what do we predict the, or what do we estimate the college GPA is for when an individual student has a high school GPA of 3.2. So it's looking here. Imagine I can draw a straighter line, and you'd want to like run across here. Because it's an individual student prediction interval, you're going to want to go with the wider one. So even just looking at these two, I mean, chances are this one's the wider one. It goes lower and it goes higher. But let me see. Yeah, that'll be it. Because 2.95, that's more of this one. 3.35, that's more of this one. So this one is the confidence interval. This one is the prediction interval. And sometimes it's hard to see where if you had like a 2.7 to 3.6, I'm obviously not the scale, 2.95 to 3.35. This one's narrower, and the second one goes out further on either end. So I'm really visual. I like to put them on a number line. It helps me see which one's narrower. But if you wanted a quick check, you could say, hey, the length of this, 3.6 minus 2.7, is 0.9. The length of this one, 3.3 minus 2.95, that's 0.4. This one's wider. So that would be another way that helps. So other issues, a really common one is extrapolation. I actually hear it a lot on the TV shows that I watch. They're very proud of it. It is something we definitely don't love in stats. Extrapolating is not a good thing. So extrapolating is when you have the equation of your line and you use that line to make predictions for values of your explanatory that are outside of what you actually observed. So, for example, if I wanted to predict the first year college GPA of a student that had a high school GPA of 0.5, so 0.5, I could plug it into the line and get the equation, it would be like 1 point something. But I shouldn't do this because if you look, so here's my x values, they range anywhere from 3.1 to 4.0. I should not use this line to make predictions outside of here. Because the idea is I don't know that outside of 3.1 to 4.0 that it's actually a line. I don't know what it does. So you want to be really careful. You do not want to do this. So you want to look at what range of values did I see in the sample. Oh, for high school GPA, I only saw 3.1 to 4.0. That means you only want to use your regression line to make predictions for high school GPAs from 3.1 to 4.0. You do not want to do outside of it. You don't want to go below. You don't want to go above. It's bad news. You don't want to do it. Let me see if I have space on this last slide. I'm going to doodle it. So one reason why I should include this example somewhere. So if you look at, what is it? Heights. So age and height. Up to a certain point, it's a very linear thing, but if you've seen a growth chart, like height and weights, they do this curve thing. But if you only have data here, it looks like it's linear. You just don't know that that relationship stays linear forever. What I mean is, if you look at my height from ages 2 years old to 4 years old, I do not grow at the same rate my entire life. So I don't want to use that data from 2 years old to 4 years old for when I'm, 35 years old. That would be bad news. So you don't want to do that. We definitely do not grow at the same rate at that point. So here, other issues, outliers. This doesn't mean you can just remove them, but know that they really can complicate things. So we're going to talk about influential versus non-influential outliers. So what we mean by influential, it means if you removed that data point, it would, significantly change the equation of your line. And most of the time, they're extreme in the x. So if you look horizontally, they're usually really high or really low horizontally. They're more likely to be influential if they're far out to the sides. It has this thing to do with leverage. We're not going to go there. So the idea is if I remove that point, so this black line is with, this red line is without, it would change the line. If I removed it, the line would move. Versus non-influential outlier, so when I remove this point, it barely shifts this line. So it doesn't really change a whole lot. Most of the time, it's extreme in the y values, but not in the x values. So it would be somewhere kind of close to the center, and it might be extreme high or low. But it's not going to be, if it's extreme in the x as well, it's more likely to be influential. So in general, this is one of the many reasons we love big sample sizes. But if you take a larger sample size, the impact from an individual outlier, it's going to have less impact on the overall model. It makes us very happy. But unless we can determine that an outlier is an error or it's from another population, it has to stay in. You cannot just remove it because you don't like it. A lot of people will do this, but it's really, really bad stats. You should never remove a point unless you have a non-statistical reason. It cannot be it messes up my model reason. It has to be another reason. So I have a flowchart for that. I threw this together. I know it's probably a little small here. It's a handy flowchart. So Step 1, oh no, you have an outlier. Was there a coding or measurement error? So, for example, I did this, I had a client who they did before and after, and they were looking at fitness in young children, and one of the measures was pull-ups, which surprised me because they were elementary school children, and I don't think I could ever do a pull-up in my whole life. But there was this one little boy, and they had recorded that they did 50 pull-ups in the time interval. And so I reached out and I contacted the instructor that recorded it, and I said, hey, is this right? Did they really do 50 pull-ups? And they're like, oh, no, that was an error. They did 5, which still beats me by a lot. But I was able to fix that issue. So can you fix it? Yes. Awesome. That's great. But if you determine it was an error, but you can't fix it, like if the teacher said, no, that's wrong, I don't remember what it was, then you have to remove it because you know it's wrong, but you can't fix it. Versus, oh no, an outlier, was it a coding or measurement error? So this could be that maybe they sent out a different person to record measurements one day, and they used the wrong tape measure. Or one thing I saw is there was a data set that for some reason they were measuring everything in it was millimeters or centimeters, and then one day one of the researchers went out and they recorded things in inches. We were able to fix that, but we needed to figure out what the heck happened because the data looked really weird. So if it isn't a coding or measurement error, we need to go ahead and determine, does this observation belong to the population of interest? So there was a time too where we saw there was like long jump or something like that, and for high school students, and it turns out the coach also participated. They weren't part of the population, so we removed that observation. They didn't belong in that observation, so we removed them. However, if you determine, no, this is from the correct, so no measurement or coding error, no, this individual belongs to the population we're interested in, then we ask this, is it influential? By the time you get to this question, you are not allowed to remove it. Not really. Not permanently. So if it's not influential, do nothing. Leave the outlier in, maybe comment, hey, we do have an outlier, but it didn't affect the results. If your outlier is influential, do 2 analyses. Do an analysis with the outlier and an analysis without the outlier and discuss the differences. Because you really, at this point, if you get to this question here, you've determined it wasn't coded or measured wrong, the observation does belong to the population of interest, you cannot remove it and not talk about it. It's past that point. You can go ahead and do both analyses, or you can do analysis with it only, but you cannot just remove it. So be cautious. I really wish that, probably cleaned up, that everybody had this type of flowchart, because a lot of people remove outliers that they don't like. Admittedly, with a student data survey, I did remove some extreme outliers. Like there was an individual that indicated they were a mechanical engineering major, and they anticipated making a starting salary of $1 million a year. Probably really unlikely. I don't know. My husband got a mechanical engineering degree. Did not start anywhere close to that, but maybe we're applying the wrong places. Okay, so here's a great place to pause. Attempt to answer this question yourself. I'm going to go ahead and work through it. So we have 3 plots. Each one has an outlier, and we want to determine out of these which is the most influential outlier. So plot 1, here's my outlier. Plot 2, plot 3. They're all a blue point, but it's kind of hard to see against the black. So for plot 1, what we want to do is say, if we remove the outlier point, which plot will have the most drastically changed least square regression line. So if I remove this point, my line's going to move to here. It's going to move substantially. It's definitely influential. If I remove this point here, this isn't going to shift much. It's probably going to be, oops, not closer to it, but really, really similar. If I remove this point, honestly, this line is pretty much going to stay where it is. So out of all of these, I would say not only is this plot 1 has the influential outlier, it's definitely the most influential out of those. So when we say which one is most influential, if we remove it, which one changes where the line would fit the most. So that's going to be it for lesson 44. And we're going to go through from the very beginning to the end of a formal analysis, looking at an example of anglerfish.